All right, welcome. Today we are diving into something pretty radical. It's a new idea from researchers at Meta AI and KAS that might just flip everything we know about computation on its head. It's called the neural computer. And believe me, it really messes with our whole concept of how a machine can think.
So take a look at this. You're seeing a video of a computer desktop. Simple enough, right? But here's the kicker. An AI generated this, completely from scratch. And that forces us to ask this really deep question. Is this AI just a phenomenal artist, just mimicking what a computer screen looks like, pixel for perfect pixel? Or is there something more going on? Could there be a real, honest-to-goodness computer simulation running deep inside the hidden layers of this network?
So here's our game plan for unpacking this. We're going to start with this idea of a ghost in the machine. Then we'll formally introduce the neural computer and what's called its latent runtime. After that, we're taking a journey through its latent space to understand the shape of thought. And we'll wrap up by looking at what this all means for the quest for true machine logic.
Okay, so to really get what's happening here, we have to completely change how we think about what that AI-generated video is.
Here's the critical insight. This is not just a movie. You need to think of it as the visual trace of a computation in action. Every single frame you see is the output of a process. It takes an input, like you clicking a mouse, processes it through some kind of internal state, and then it generates the new screen. We're not just watching a recording, we're watching the footprints of a system as it runs.
So this whole idea of a computational system that's literally baked into a neural network, well, it has a formal name, thanks to its creators at Meta AI and KASUT.
They call it a neural computer, or NC for short. And the core idea is pretty wild. Forget separate chips for the processor, the memory, the inputs and outputs. In a neural computer, all of those things, computation, memory, I/O, they're all fused together into one single, dynamic, learned state that lives entirely inside the model.
Okay, so how does this thing actually work? Well, you can think of it like a continuous loop. It's really just a few steps. First, you start with the system's previous internal state, where it was a moment ago. Then, step 2, you give it some new info, like a user clicking the mouse. Now, step 3 is where the magic happens. A function, they call it f theta, takes that old state and the new input, and it calculates the next hidden state. And finally, step 4, another function, g theta, takes that brand new hidden state and basically paints the next video frame for you to see. And that's it. That loop, update the state, then generate the frame, it's the very heartbeat of this neural computer. But you know, the video we see, that's not even the most mind-bending part. The really fascinating stuff is happening inside that hidden state, in what the researchers have dubbed the latent runtime.
This sentence is everything. The video of the desktop, it's just a shadow on the cave wall. The real program, the actual computation, is the journey of this latent runtime state. Think of the screen as just a decoder, a little window giving us a peek into this massive hidden reality that's unfolding inside the model.
So what this means is, the video is not the program. The program is the dynamic evolution of this hidden state, which they label as HT. Your mouse clicks aren't just pushing pixels around, they are direct commands into this invisible internal world, literally steering the program as it executes. To really wrap our heads around this, we're going to need a new way to visualize it. We need a metaphor for this hidden world.
So imagine for a second that at any given moment, the entire state of this neural computer, all its memory, what it's doing, everything, can be represented as a single point, just one location.
Now, this point isn't just floating around in nothingness. It exists inside this vast, incredibly high-dimensional landscape. Picture a terrain with hills, valleys, and all sorts of complex geometric shapes. This is the AI's internal mindscape. This is its latent space.
So what is a computation or a thought in this world? It's not a string of ones and zeros anymore. It's movement. A computation is simply the path that our point takes as it travels across the surface of this hidden landscape.
And what's steering it? What's guiding this path? Well, that's where that f theta function comes back in. It acts like a learned vector field. Basically, it creates currents or winds all across this landscape, telling the state point which way to move from any given location. And your inputs, like the mouse clicks, they act like a rudder, tweaking those currents to steer the point along a very specific path, a specific computation.
This leads us to a really critical realization. The actual shape, the geography of this internal landscape is everything. But why? Why is it so important?
It's because the geometry of this space literally defines the computer's behavior. Stable, predictable behaviors like what you'd expect from a calculator app, they correspond to valleys or low-energy regions in this landscape. The researchers call them manifold attractors. The state point is just naturally drawn into these valleys, which is what makes the computation robust and reliable. It's just like a ball rolling down a hill. It's always going to end up at the bottom.
And this right here is the key difference. See, a classical computer, its state is just a long list of ones and zeros, right? Its whole world is like a grid, and the program is just a rigid, explicit set of rules. But a neural computer, totally different ballgame. Its state is a single point on a smooth, continuous surface. The space is this incredible geometric landscape. And the program, get this, the program is the learned shape of that landscape. So programming it isn't about writing lines of code. It's about literally changing the geography of its mind.
Now, of course, we're still in the very early days here, and the researchers are super clear about the current limitations. When they actually tested the model on its ability to do simple arithmetic natively, to really compute the answer, not just show what it looks like, its symbolic accuracy was only around 4%. And what that tells us is that right now, the model has learned the appearance of computation incredibly well. It's an amazing renderer. But it hasn't yet learned to carve out those deep, stable valleys that you need for real logical reasoning.
But look, that limitation doesn't take away from the vision here. It just helps us see the massive challenge that lies ahead.
The end game, the ultimate goal, is what's called a completely neural computer, or CNC. We're talking about a system that's universally programmable and behaviorally stable, just like the computer on your desk. But the real holy grail here is creating a machine-native programming language, finding a way to give it instructions, not with code, but by directly shaping the topology of its internal latent space.
What this all means is that the grand quest for the next generation of AI might not just be about making bigger and bigger models. The real challenge is one of topological engineering. It's about figuring out how to precisely sculpt these internal landscapes, how to carve the valleys and forge the pathways that create stable, complex, and totally reliable machine logic.
And that leaves us with this final, truly mind-bending question. What does it even look like to write software for a machine like this? How on earth do you program a computer whose native language isn't logic and symbols, but the very geometry of thought itself? That's the frontier we're just now beginning to explore.